Hi everyone, I'm Ling Hui Luo, a PhD student from Paderborn University in Germany. I am very honored to be selected for this student research competition. Today, I want to introduce you a general approach to modeling Java framework behaviors. Every year, cybersecurity groups such as OWASP publish lists of damaged vulnerabilities. Many of these vulnerabilities can be actually detected by varieties of static data and data flow analysis. In this talk, I will focus on sensitive data exposure, which can be detected by taint analysis. How does taint analysis detect a data leak? Taint analysis finds sources and sinks of sensitive data and reports a data leak if it finds data flow between them. Sources are basically code where sensitive data is read, for example, getting the current GPS location. Sinks are code to communicate the data, for example, sending an SMS. Since the source and the sink are in different methods in this example, it requires the taint analysis to be inter-procedural, so it needs global information about which methods are called. A call graph can provide such global information. It represents the calling relationship in the program. This data structure is required by every inter-procedural data flow analysis. Given the call graph, control flow graphs of each method can be combined to build a ICFG. The ICFG can be then used to track data flows from sources to sinks throughout the program. From the last example, I hope now you got a sense how important call graphs are. In real-world applications, constructing a sound call graph is challenging because many software applications nowadays are built on top of frameworks, such as the Android framework for mobile apps and Spring framework for web apps. These frameworks commonly use dynamic language features such as reflection or dependency injection, and the interaction with the application code is spread through many functions in the framework. So here is a malicious taint flow from a real-world malware Android app, which leaks users' last known location to a malicious server through a HTTP request. There are 8 essential lines of code in these slides that need to be analyzed in a flow-sensitive way, which are distributed, as you can see, in the method of 3 classes that are subtypes of classes defined in the Android framework: an activity, a service, and a handler. If you analyze just the Android app without the framework, you will miss the leak, since none of these methods you see on this slide are actually called in the application code. The actual call graph at runtime looks like this. The Android framework scans the app and determines which classes needs to be initialized and which method need to be called. So, effectively constructing a call graph that covers all the application code is the key to the analysis. Since the frameworks are usually very complex, most analysis tools nowadays don't analyze them but rather model them by adding these edges artificially based on framework documentation. However, such modeling is tedious, error-prone, and quickly becomes outdated. Since there are many frameworks, we avoid precise modeling of every one of them. We need an approach that is generally applicable for Java frameworks. Our work is inspired by errors from Ali and Lotek. The idea of errors is to generate a lightweight placeholder library that models the original library and then use it for call graph construction and pointer analysis. Errors generates the placeholder library based on the separate compilation assumption, Basically, it means that the library doesn't know the application when it is compiled, which limits what it can actually potentially do to the application code. Since frameworks are just fancy libraries, you might think, why don't you just use arrays? Yeah, as much as we would like to do so, it turns out that the arrays creates too imprecise models that are actually not suitable for taint analysis. Here you see the placeholder classes generated by arrays for the previous example. This model simulates what the original library could potentially do, such as create objects and invoke library callbacks using a do-it-all method. It has every call we need for detecting the data leak in the example. But they are invoked, as you can see, in arbitrary order. The 8 essential steps do not appear in the right order. A flow-sensitive taint analysis will still miss the leak. To solve this problem, we extended the model by adding 3 kinds of edges to model control flow. So we don't precisely model which method should be called in which order, so we adjust control flow edges such that every possible call sequence is covered. The red and the blue skip edges, as you see on the right side of the slide, allow to skip invocation of a method. The green loop edges simulate the effect that a method can be called multiple times. By using these control flow edges labeled with A, B, C, D in the example, we can analyze then the 8 steps in a correct order. Another problem is the placeholder library generated by arrays uses one field called libraries point to abstract which objects the library can point to. Once this field is tainted, every object that the library can hold reference to will be tainted in the taint analysis. Obviously, this is too imprecise. So we need to separate this field. So what we did is that for each type, we generate a field that abstracts all the objects of that type the library can point to. This way, we don't prove the object of other types that much. This might be unsound, but it turned out to work well for detecting real-world issues. Here, you see another problem. Because arrays was designed to be very conservative, so it assumes that the library can create objects and call methods in every library method. So it creates objects repeatedly. But in this example, we need actually the typed library point to field to stay tainted in the do-it-all method. However, it is overwritten by a newly created object, which means the point-to relationship should be removed from the analysis as it no longer holds. This is the so-called strong update. A precise taint analysis usually considers this, which leads to the typed library point to field untainted. To solve this problem, we move the code for creating objects from the do-it-all to a separate main method, which is called only once. Based on our experience, most objects of application classes are only created once by the framework. We evaluated our approach with a precise client taint analysis called FlowDroid. We modified FlowDroid to use call graph constructed with our approach using the generated placeholder library for Android. We run both tools on Taint Bench. It is a benchmark suite consists of 39 real-world malware apps with a documented baseline ground truth. The ground truth documentation of Taint Bench contains both true positive cases and false positive cases that can be used to access a tool's precision and recall. As you can see, the recall, our version of FlowDroid detects 11% more problems in Taint Bench in comparison to the original FlowDroid. Although it produces a few more false positives, the precision is still improved because proportionally it detects more problems. So in total, both precision and recall are improved, showing our approach is very effective.